How's it going, everybody? So today we're going to be talking about transformations of a square root and a cube root. You'll notice I have the parent functions of both of them side by side. So let's go ahead and take a look at the square root first. So you'll notice the square root, okay? I went ahead and put the table down at the bottom. You'll notice we're only observing between the numbers 0 through 4. The reason for that is because the way a square root works is it doesn't exist to the left. Unless we do a transformation, of course, but for now it doesn't go to the left because if we have a negative inside of a square root or an in value that's even, it becomes imaginary, and so that wouldn't exist within the real numbers plane. So if I was wanting to go ahead and plot this, you'll notice the square root of 0 is 0, which is why we start at the origin right here. I'm doing it in blue. And then the square root of 1 is 1, so we go to 1. You'll notice the square root of 2 is 1.41, so slightly halfway. And then the square root of 3 is 1.73, so a little bit higher than halfway. And then the square root of 4, we're more comfortable and familiar with that one, that is 2. Okay? And so if we were to trace our graph, it would look something like that. Okay, and of course, try to make your little circle's a little bit better than mine. Now, you'll notice on the next one for the cube root, we can actually observe the left and the right hand side. So that's why we're starting at -2 going to +2, because you can actually take the cube root of negative numbers, okay? Now let's go ahead and plot them. So -2 goes to -1.25, about right there. And then we have the cube root of -1 is -1. And then the cube root of 0 is 0. Cube root of 1 is 1. And you'll notice it repeats itself. And then the cube root of 2 is going to be 1.25. And so what you'll notice is the shape it kind of retains is this little S-looking shape right there. Now what we're going to do is we're going to go ahead and apply the transformations to each parent function, okay? Now these transformations are very straightforward, okay? And we'll knock them out. So let me get everything out of the way real quick. Alrighty, there we go. Now let's talk about, we were wanting to transform the square root, and let's say we wanted to move it to the left, okay? In order to move it to the left, that would look something like this. Y is equal to the square root of x plus 2, okay? Now if we wanted to move it to the right, it would look like something like this. Y is equal to the square root of x minus 3, okay? So the big distinction, of course, is the plus and then the minus, okay? Now, of course, the way this would look is, since we did x plus 2, we'd go 2 to the right using the origin, okay? So I based everything off the origin for this sketch. Now, of course, when you have that table, you can make a better graph, but for now we're just doing sketches, and so it would still tail off to the right. Now, if you went ahead and went to the right, you'd go 1, 2, 3, okay, with that origin, and then you'd move over. Now, of course, you would just add 3 to each one of those x values, and then you'd see it would do the same thing, okay, for the table. Now, let's say about we want to go up or down. All right, here we go. Got up over here. Let's go down over here. Now remember, that initial one, that was called a horizontal translation. This is called the vertical translation, okay? Now, this will look like y is equal to the square root of x plus, let's do 4. And then we'll do y is equal to the square root of x minus 1, okay? So if we were going up 4, you'd go up in the y direction. So 1, 2, 3, and 4. And then it would shoot off to the right. And then for the minus 1, you'd go down and then over. Oh yes, if you hear my dog acting crazy, it's because she's been quarantined for a while too, and she's going turbo right now. So if you hear her running around the house, that's because she just can't help herself. Alrighty, back to math though. Alrighty, so that would be up and down. Pretty straightforward. Now let me think. I guess we can now move on to the reflections. So let's go ahead and do that. Let me erase this. Alrighty, so now we have across the y-axis, across the x-axis. Now, believe it or not, we're going to see a lot of change when it goes across the y and the x, okay? Now, for it to be across the y-axis, remember, it depends on where the negative is located. If the negative is located inside next to the x value, then that means it's going to be a reflection across the y-axis. Now, if the negative was on the outside, okay, then that means it's across the x-axis. Now, since it's across the y, what that's going to do is, and I'll go ahead in, I guess, a different color in blue. This was the original, okay? It goes like this. Okay, that's what he originally does. But when it's across the y, he now does this. Okay? And if you'll notice, it kind of makes sense. I mean, if you were to fold that across the y-axis, remember, this is the y-axis right here. If you were to fold it across this y-axis, it would basically fold over to that side. And that does make sense, right? Now, for the x-axis, okay, I'll go ahead and draw the original. It's like that. Now, if I were to reflect him, that's across this right here, this x-axis, that means he now looks like this. Pretty cool, huh? Now, for those of you who are maybe inquiring, like, what happens if you apply both of them? Well, let me show you. So let me erase this real quick. So here's what would happen if you did both. So if you were to do this one, where you have y is equal to negative square root of negative x, the negatives are in both places. So transformation, in how we would write it is we'd say there's a transformation across the y-axis and a transformation across the x-axis. And how this would look is what the y-axis would normally do. So, starting with the x-axis, remember the x-axis, what it does is it makes it flip down, right? And then the reflection across the y-axis makes it flip across. And so for its final debut, it'll be down and over here. Okay, so and just to kind of show, this green one is where it started. So the green one is the parent function, where it normally looks like its base. The red is the reflection across the x-axis, and then the blue is a combination of it retaining that attribute of the x because it's flipped across, but then also now applying the y-axis. So you'll notice how it comes full circle, okay? So hopefully that maybe gives you some insight about how both can be applied. Alrighty, so that was the reflection. So let me erase this right now so that way we can talk about the stretch and the compression now. Alrighty, so in order to talk about that, okay, we need to know the A value and what it means. So if I'm talking about a stretch, that means that my A value is going to be greater than 1, right? He's got to be bigger. And we can't say equal to 1 because if you multiply anything by 1, you really haven't done anything to it. So that would be something like y is equal to 3 square root of x. Okay, now to be more precise, I should have said this. This is vertical. Okay, this is your vertical stretch and your vertical compression over here. Now, the reason why these are considered vertical is because this type of transformation is happening outside of the square root or outside of the parenthesis, right? If it was inside of the square root or inside of the parenthesis, that would be a horizontal, and that's going to cause us to have to change our way of thinking a little bit, right? Now, looking at this vertical stretch right here, what would that necessarily do to our graph? Well, it would literally stretch him, right? So he'd literally go from being like this to now like this. He got stretched vertically. You pulled him upward. Now, a vertical compression, okay, so something like y equals 1/2 square root of x, that would just make him really super skinny. Like, you'll notice the bigger the fraction you end up putting, the closer and closer it's going to want to get to the x-axis. So it's really interesting. So like for instance, if you're typing into Desmos or something, you could try something like really small, like 0.1 or something, like a 10, 1 over 10 maybe, or even like 1 over 12. And you'll notice it just gets closer and closer and closer. And you can almost make it look like it's hugging or on top of the x-axis. Now let's move towards the horizontal stretch and the horizontal compression. So let me erase all this. Alrighty, and also too, something I wanted to mention, when you're going back to that vertical, add this little note. So for the vertical compression, you want to make sure that the A value is going to be greater than 0 but less than 1. Because if it once again was equal to 1, it wouldn't be doing anything. But since it's less than 1, it's going to start compressing it vertically. But it's got to be greater than 0, because if you just multiply it by a 0, then the whole function goes to 0. So we haven't done anything to it besides making the whole thing disappear off the graph. So just be aware of that, okay? And I'll make sure to use that notation here. Now, looking over here, a horizontal stretch in this scenario would be something that looks like this. Y is equal to, oh, gotta get my pencil out. Y is equal to the square root of, let's say, 0.1x. So that's not a negative, that's 0.1, okay? So 0.1x. And remember, you have to think literally what it means to stretch something. If I'm stretching something horizontally, that means I'm pulling in this direction, right? I'm pulling my parent function horizontally. And so remember, the parent function looks like this, right? But if I were to stretch that thing horizontally, he would start to stretch and he'd get skinnier. Okay, and that almost sounds counterintuitive, but that's the case, right? And so for it to be a horizontal stretch, that means the A value being inside the square root has to be greater than 0, but less than 1, okay? Now, the horizontal compression, that means now we're pushing in, okay? We're compressing him. And so think about it. If you were to compress this parent function, what do you think he would do? Well, he would get super tall because you're pushing in on him, okay? You're pushing him towards that y-axis. And so you would have y is equal to the square root of, I think a noticeable change, you could probably do like a 5. And I think you would probably see something, a really good horizontal compression. And so remember, that's when you have an A value, okay, that is greater than 1. And so there you go. Those are the horizontal compressions and horizontal stretches of a square root. Now let's talk about a cube root, and you'll notice that we're going to apply these types of transformations once again. So we'll go through it pretty quickly. Okay, so let me erase all this. Alrighty, so say we wanted to go now, starting all the way at the beginning, a horizontal translation of a cube root. So we wanted to go left or right. It would look something like this. So y is equal to the cube root of x plus 1, and then y is equal to the cube root of x minus 2. Okay, so you'll notice a lot of similarities here. So plus 1 would be this direction, and so he would go like that and like that. To the right 2, he'd go to the right, and then boom, and then boom. Okay, pretty straightforward. Now let's go ahead, let's show about up and down and get rid of that real quick. Okay, now up, down. So we've got the y is equal to the cube root of x plus 2, and then y is equal to the cube root of x, let's say minus 1. Okay, so right here for the plus 2, we're going to go up 2, so we're up here now, and we go here, and we go here. The only difference is we got an S guy, right? He looks like an S. And then down 1, So we have like that square root part, but then we have the cube root part, his tail, okay? Now let's talk about, so the reflections. Aha, that'll be fun. Let's do the reflections now. So if we were talking about a stretch, it would look, and I'll put that here. Remember, this is the vertical stretch. This is vert. And this is vertical compression. All right, so a vertical stretch, that'd be y is equal to 3 cube root of x. Okay, so what that's going to do is literally stretch the look of the s. So it'll be up and higher like that. So he was stretched vertically. Now that's, remember, when your a value is going to be greater than 1. Now over here we have a compression when y is equal to, I don't know, 1/2 cube root of x. Okay, and so our little s here now gets skinnier. Okay, and that's when the a value is between 0 and 1. Okay, now let's go ahead and take a look at the horizontal. Ready, there we go. So let's see here, horizontal. And then stretch. Okay, now it's going to migrate its way inside. So we have y is equal to the cube root of, and then that'll be like 1/2 x, right? Remember, it's got to flip. So our stretch is between 0 and 1. And a horizontal compression, okay, is looking like this, where it's greater than 1, okay? So let's go ahead and draw those graphs. So we have a stretch horizontally, so we're stretching him horizontally, so he got skinny. And then we're compressing him, so he's gonna get larger. Oh, whoops, probably should draw him a little bit more like that. Okay, now these graphs are not done beautifully, but I'm trying. There we go. Now let me circle back around. I done goofed in this video. I was editing the video and I said at some point in time, let's talk about reflections. And then all of a sudden I started talking about stretches and compressions. And you're probably sitting there going, Mr. Farmer, that was bad. I know, my apologies. But because this video is so awesome, we're not going to change it, okay? We're going to keep moving forward, okay? And it also doesn't help that Mr. Farmer's not technologically advanced enough to know how to edit a video like that just yet, but one day I will. But, once again, I digress. Let's talk about reflections officially. Oh, and in the proper color. We've been doing it in red. There we go. Reflections, okay? Now, we have reflections across the x-axis and then across the y-axis. All right. So, remember, it depends on where the negative is. So, if we have y is equal to the negative cube root of x, that's what it looks like. And for the y-axis, it's y is equal to the cube root of negative x. So, once again, depends on where the negative is located. So, start kind of going back to the x-axis. If we distribute, or not distribute, but have the negative on the outside, that's going to make my graph do this. Okay, it's going to reflect across the x-axis. Now you might be wondering, well, what am I basing that off of? Remember, the parent function looks like this. Okay, this blue dashed one. Okay, so you've reflected him, sandwiched him across the x-axis. And for the y-axis, I'll go ahead and draw the parent function so that way you can compare. Now let's draw the actual function with it reflected, and it looks like this. And you might be going, whoa, Mr. Farmer. You just drew the exact same thing. It looks like the reflection across the x-axis and a reflection across the y-axis. What did you gone done and did? Well, the truth is it actually is the same thing. Believe it or not, if you try to reflect across the x-axis or the y-axis, it will look exactly the same, okay? Now, you might be wondering this next question, though. Well, Mr. Farmer, what happens if you do both of them? Well, let me show you how that works. All right, here we go. So let me break this down step by step. So we have, and I'll try to use different colors. So let's start with the original parent function, okay? And I'll use more colors. Let's do more colors. So I'll start with yellow. Yellow sound good? So the parent function looks like this, okay? That's what he normally looks like. However, let's go ahead and do the initial flipping it across the x-axis, okay? So what that's going to do, I'll put that in green, is this section right here, and I'll kind of highlight maybe. I'll try to do some highlighting. So this section right here, okay? Flip it across the x-axis, it's now here, okay? And then when you flip this section right here across the x-axis, he's now here, okay? And that just makes sense. If you were to flip it across the x-axis, that's where you'd be. Now I'm going to draw my green line over here, okay? So that's the x-axis. Now, let's take this green part, okay, right here, and I'll do blue. So this bit right here, and let's flip him across the y-axis. So flip him in this direction across the y-axis, right? We're going this way. That's across the y, right? Terribly drawn arrow, but across the y. And so now he's over here. Okay? Now let's then take this piece right here and flip it across the y-axis. Now you understand, in order to flip him across the y-axis, he has to go in this direction. He's got to go that way to go across the y. So now he's over here. Well, if you look at this, guys, this right here is the parent function. Look, it's, if I were to highlight the yellow and you were to look back at the yellow, don't this yellow highlighted part and this part over here, don't they look the same? They should. So, yes, doing the reflection across the x-axis and the reflection across the y-axis, they simplify each other. Believe it or not, they revert back to the parent function. That's kind of cool, right? Alrighty, guys, that's it for the transformations. Let me know if you have any questions or concerns. I'll make sure to try to answer them. And yep, just let me know. Alrighty, bye, guys. You have a good one. I flip through these. Does it cause new videos, or does it